All right. So I hope everybody is able to hear me. Good, good. All right. All right. So let's start now. So first of all, I'm extremely sorry for the delay. There are some connectivity issues. So expect some problems today. And all right. All right. All right. So let me open up the second sessions. All right. So we were discussing till last session, we were discussing about these problems. Okay. I see some of you have attempted the MapReduce problems. Others are yet to attempt. So let's just go over the various problems where we left yesterday. I mean on the last weekend. Okay. So Priyabharat is not able to hear me. Is everybody else able to hear me? Good. 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 So everybody else is able to hear me, so no problems. All right. Great. All right. So let's go one by one. And also, let's go one by one over the problems. Then we will discuss other parts. All right. All right. So the first problem where we left on last time is the frequencies of letters. If you have to compute the frequencies of various letters in a big file, do you need MapReduce? Okay. Do you need MapReduce? All right. So without the MapReduce approach, so before we discuss the problems, do you have any questions for me? Yeah. Yes, I have started the recording. All right, Richard. Good, good. So coming back to the problem here, let's say there is so if you have to compute the letters frequencies of the letters in a file, you could easily do is you just create an integer array of 26 size and then scan the text character by character in a big file and increase A0 if you encounter A and increase A25 if you encounter Z. All right, this is capital A, this is capital A. All right, okay. So, all right, so everybody agreeing with this approach? So the idea is to compute the frequencies of letters, and in case we use a normal without the MapReduce approach, this would be probably the easiest approach to do. We basically maintain 26 numbers, okay, and count the occurrence of each of the alphabet. All right. Now, what would be the problem in this? Anyone? Okay. Yeah. So here, the problems, as some of you have said, uh, although the problems will not be the usual one, the RAM will not be a limitation because we are not maintaining too much of data in the memory. But network I/O or disk I/O will be the bottleneck. All right. CPU may be the bottleneck, but not necessarily. Okay. CPU may be the bottleneck, but not necessarily. Okay. So you are right, Michael. So CPU will most likely be not the bottleneck unless we are doing some computation. So I don't think this will be the bottleneck because we are not doing any major computation. Okay. Everybody agreeing with this? So the disk IO, as in the time taken to do the read the file from the disk, is going to be the problem, right? What else do you think the problem would be in this approach? Anybody? Is the approach clear to you? This particular approach we're talking here? Yeah. So it's clear to Anuj. I'm assuming that it's clear to Michael as well. All right. So if you think about it, if you do back of the envelope computation, the main time would go in reading from the disk. All right. So if you have a gigabyte of data, it will take minimum of 5 minutes to read 1 gigabyte of data from the disk. So you cannot, no matter how great computer you have, you cannot do a better than 5 minutes. You cannot compute the frequencies of letter in a gigabyte of data in less than 5 minutes, right? Unless you use multiple hard disks and parallelly compute the frequencies of parts of the data parallelly over the network, right? Good, good. Do I make sense? So for when the data grows, say beyond a gigabyte, then probably distributing that gigabyte data over the network would make a lot of sense. Okay, let's do a little bit of computation. Let's say we have 1 gigabyte data, and we have divided that into 8 blocks, right? Now on each 8 of the blocks, we have 128 MB each, right? Now if each of the 8 computers is doing the computation, each of them is parallelly taking 5 minutes divided by 8. All right? This much of time in IO. All right? It's being done parallelly. Make sense to you? So on an average, if you have put 1 gigabyte of data on the cluster and you are trying to compute the frequencies, the time taken would be reduced by 1/8. All right. Now, although the time taken to do the computation parallelly on each of the block would reduce to 1/8, there will be a little bit of an overhead in starting a MapReduce job and getting it done. So if you assume that total time will be 5 minutes divided by this plus 1 minute, okay? All right? So basically, after a gigabyte of data, it would make sense if you do a back of the envelope calculation quickly. So roughly, if your data is going beyond a gigabyte, specifically for computing the frequencies of ladder, where the result of doing the frequency computation does not take much time to travel from one node to another, right? Because if you imagine that there are 8 computers in parallel and all of them did a frequency computation, and then you sum it up on each node, and then you count the frequencies later point of time, then I mean some there'll be a transfer cost, of course. Shuffling will be there. Okay, I'll describe to you in detail. Okay, so after a gigabyte or so, MapReduce will make sense. I hope. All right. So, are you able to hear me? Hi. Are you able to hear me now? All right. All right. So, I just hope my internet works for some more time. I have three network connections, and in today, none of them is reliably working. Yeah, yeah, I know that. Yeah. All right. All right. Again, extremely sorry. I hope we do not get disrupted again because in Bangalore there is a bad uh, the power outages. Because of that, these network connections are not working for correctly. I have three connections and none of them is working properly. I hope this one works for some time. All right. Okay. Okay. Let's. So again, let's just go over the frequencies of the letter. How would you use the MapReduce to solve the frequencies of letter? The most rudimentary approach would be to do the MapReduce exactly the same way we did for word count problem. Meaning, in case of word count problem, we made key as the word and one as the value. Here, we could do the same thing, as in the map, we make the letter as the key and we can make one as the value, and in reduce we could do the summation. Okay, so for example, for each, if in case of in each mapper, if we could convert the text into the frequencies of the letter in that line, then we would get something like this. All right. So mapper 1 will give out the frequencies of the letter in it encountered, and mapper 2 will again do the same thing, and so on. And after these frequencies of the letter in various lines get merged together, in the reducer, we will have the group by, and then we'll do the summation. Okay. So do you want me to describe this approach in detail? All right. So some of you have asked to describe, most of you have got it. Okay, so the clear idea is, let's say this is a bird. Okay, uh, and just give me some more text to do some things. This is a bird that lives in a tree. Okay, and let's say there are two lines and there are more lines in this. Okay, so each line will be fed to the mapper. Each line will go to the mapper. Okay, say mapper 1, and this will also go be fed to the your mapper function. And what does your mapper function do? It'll take this text, convert it into something like this: t1, h1, s1, I1, and so on. Okay, similarly, again your mapper function will take the line and then convert it into the something like this. All right. Or if I have to do it quickly just for demo purpose, all I have to do is replace each letter If you guys have gone through my regular expression session, how many of you have gone through my regular expression session? Okay, so you could simply use something of this sort. All right, you could say um, this tab one, and then slash n. So I converted all of this into, okay, so you can see that now. All right, and then so our mappers on every node converted the input into character 1, and so on. Now Hadoop took this output, the output which is given. Hadoop took it, sorted it, the one, so Hadoop sorted the data, and after the Hadoop has sorted it, then it is given to your reducer phase. And what does reducer do? Reducer basically would take letters and do the computation. Okay, so this is okay. Yeah, I think a better thing to do will be like this. All right, so you can see that a, the space has occurred 7 times, a has occurred once, b has, and so on. You can see that. So this is the way you can compute the frequencies of the letter. There are many optimizations that you could do. We will go into the details because each mapper is converting, each mapper is producing the key and the value, and that's getting shuffled and getting transmitted to the reducer, right? So if you see, if you see here, so reducer is getting that much of data. Okay, instead each node could have computed just the frequencies instead of giving the list of all the letters, right? To do that, we will use something called combiner at later point of time, so that most of the summarization would finish on the node itself. It's like running a local reducer before transmitting the data from all other mappers to the reducer. Okay, that is called combiner. We will discuss it again at a later point of time. All right, so Karthik is saying that in the mapper, I guess the value is not 1, it is incremented for each occurrence. So yeah, there are two approaches. One is that we compute in the mapper, we compute the frequencies of the letter in the sentence and then print the frequencies here itself. Okay, for example, we could do t, how many times quickly? 1, h 1, and I 3. So our mapper, when given the input from this, could basically either compute the frequencies or print uh, print simply the way we did the word count. Okay, so either way. Okay, so you could do one level optimization by computing the frequencies in each sentences in each map. Again, map map function gets a single line at a time. Now map function can your map function can a either print character 1 as in key value, okay, or in the key value format it can also start doing the computation and start printing the frequencies itself that it encountered. Just it's a one level of optimization. All right, and all the results will get to the reducer, and there it will get the it will get the you know aggregate it together, and the result will be there. The most important part which we will discuss when we discuss about combiner, how to make this process faster, so that from each mapper node, when the shuffling is happening, okay, when the shuffling from each mapper node happens, only the summary goes to the reducer instead of the full alphabet list. So, all right. Now, good, good. Now, let me answer one question which is very important at this point of time, and after that, we can. Here is a question from Michael. He says that what breaks data up into the chunks for the mapper, the job tracker, or the name node? Okay, good, good. So, the process is like this. The file which we are trying to read is is already broken into blocks, right? And for each block, our mapper will be created, and inside each block, okay, and inside each block, there will be records, okay. So inside each block, the records will be created on the mapper node, on the, you can say, task trackers, or wherever the mapper is being, okay, on the node where the where the block is located, okay, by map reduce component of Hadoop. Okay, so file is already so what we are doing, we are given our map reduce program is given a big file, right? So we give this big file to the Hadoop along with our mapper and reducer logic. Hadoop takes this file name from you, and finds out where is this file located in HDFS. Where are the blocks located in HDFS? All right. And these, for each block, wherever it has found the block, it will create the mapper instance. And when it has created the mapper instance for each of the block, okay, afterwards, each of the block is loaded, each of the block is converted into records, right? And for each record, our map function is called. Okay, does it make sense to you? Yes, that's correct. So for each mapper, that's the next follow-up question from Michael. So each mapper receives one block at once. Yes. Oh, okay. So each mapper receives one record at once. Okay, record at once. Because our map function will be called against a record. And the record in case of plain text file is a record in case of plain text file is a line, right? A single line. All right. Yes, a record is a further division of a block. That's correct. That's done by this process of breaking down of or converting, okay, the process of breaking down each blocks is part of MapReduce framework. Okay, we will go into the details how a block is converted into how a block is converted into records. That we'll go into the details later. But right now you understand that in case we are dealing with a plain text file, the blocks of data, blocks of plain text file will be converted into one line per record. There will be one record for a line. A record means a line, and for each record or for each line our map function will be called. All right, so basically you will have to write the map function which can convert into record into a key value pair. Okay, so basically a record is fed to your map function, and the output of map function is a list of key and values. Key is something on which you want to get your data sorted. All right, and the reduce function is your reduce function again is something which takes key and list of values for that key. Okay, and then returns anything, as in generally aggregates, maybe. Okay, and it gives the output, so it's up to the reduce function what it wants to give out. Okay, all right, I hope this was a quick all right, there are few more questions. All right, there is another question from Sanjay. So for each block, there are n number of mappers depending on the size of the file. So for each of the file, there are n number of mappers, and for each mapper, there will be okay. Let me put it this way. So for each block, there will be one mapper instance. Okay, one block, one mapper instance. Okay, and it might have m number of records. Okay, and for and that means m times will be calling the map function. So each mapper has a map function. Each mapper has a map function, and that map function gets called many times, but the instance of mapper is created only once. Okay, all right, good. So again, thank you, Vidya, for repeating what I'm saying. So yeah, this is good. Map function is contained in a loop and is called every time a line is read. Yes, that's how you can visualize. You can visualize that inside the Hadoop, there is some for loop which is going through record by record, and for each line it's encountering your map function is being called. Okay, that's how you can visualize. Good. All right. Next question is if the file is small and 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 block if the file is stored into multiple data nodes. Uh, okay, if the file is small, so there if the file is small, then there will be only maybe one block. So All right. Lakshman's question is, all right. If there are, all right. So, so if there are n blocks, and each block has m records, total number of times the map function gets called is n into m. All right. Good. I hope that clears for you. Karthik's question is Karthik's question is good. Let me put it here. This is a good question, and we will answer this when we discuss more about the readers. Okay. So Karthik's question is, where is it configured that a record is a line? Okay. So when we discuss about input readers, okay, text input reader and various kinds of input readers, you will get this answer. All right. You'll get this answer when we look at the Java code. You will, that time you'll wonder, why have we mentioned that particular line which says that our input format is text? Okay. You'll get that answer that time, and we'll go into more details when we discuss that. Brilliant. All right. Good. So Lloyd's question is, if the block is replicated in 3 copies, will the mapper function will run for each block? If a block, no, no. Okay, so mapper will not be, if a file is having 3 blocks and these 3 blocks are, okay, let me put it this way. This is a little eh, interesting question. Okay, so if a file is having 3 blocks and each block has replication factor of 3, okay, how many mapper instances will be created? Anyone? That's correct. There'll be 3 mapper instances. Okay. Now, there'll be 3 mapper instances. All right. Now, you might wonder that then what's the point of having replication factor? Can't we utilize that? It does. It does. First, out of 3 copies of each block, it has to pick up one node which is mostly free, right? So out of three replicas of a block, it will pick up the block which is mostly free, because the task tracker knows, sorry, the resource manager knows clearly that which node in the network have been assigned what, and based on that it will pick up the node which is free. It will pick up the node which contains the block and is fairly free. So out of 9 it will pick the 3 nodes which are mostly free, doing nothing, and based on that it will create the mapper on those. Does that answer your question, Lloyd? Now, great, good question. Now moving ahead. So yeah, with the, I missed your question. Could you copy and paste it again, please? Are you able to do that? All right, we have got one question from Tushar. All right, and let me put it here. The file to block mapping on the same node on the name node is stored on the disk. The locations of the blocks are not written to the disk. The file to the block mapping, okay, is stored on name node. That's correct. The locations of the blocks, yeah. So this was an optimization done at later point of time. Okay, so this was an optimization done at later point of time to avoid the. Uh, this was done in order for the something called federation or block cache. Okay, so this is a good question. Thank you, Tushar. All right, so there is something called block cache, which was which became part of the design in HDFS. And as part of that design, the blocks were being uh, sort of utilized in case of name node federation, meaning if you have multiple name nodes, you will have the same data nodes containing the blocks. All right. Now, in order to make it really seamless and let each data node manage the location of each block. Okay. So what name node started doing is it stopped persisting the information that where is each block. Okay, where exactly is each block on the data node. All it kept was that these blocks are on this particular name node, and okay, these blocks are on this data node, but it did not kept an account as on that where exactly, I mean, where exactly are the blocks? Okay, it just kept tracking that these are the various nodes. So as soon as the name node comes up, it talks to all the data nodes available and gathers the details about block to file to block mapping. So that was an optimization done in order to reduce the headache of the name node. Okay, all right, great. Great. All right. And yes. Now, the next, there is a question from Rajesh. In this case, the name node should be knowing which active node that is used. Yes. Name node does not need to know which active node is used for computation. Instead, the resource manager, or you can say the job tracker. Okay. Job tracker of Hadoop 1 is known as resource manager of Hadoop in Hadoop 2. And in Hadoop 2, the the resource manager knows that which node is busy. So when you schedule your work that I want to compute the frequencies of letters in this particular file, you take the text file name and you write your map function, you write your reduce function, hand it over to the resource manager and say that I want to run my map reduce. Now, as part of that map reduce framework, the query goes to the the MapReduce framework will ask resource manager, which in turn ask name node that can you tell us that where all this file is located. Now name node returns a list of all the blocks that these are the 9 blocks for your file, where there are basically 3 blocks and each of these blocks are replicated thrice. So there are effectively 9 blocks and here is the list. Now, the call goes back to the resource manager, and resource manager decides, looks at the list of all the nodes which are busy, and out of each of the three replicas it picks up the one which are comparatively free, and then it starts the map reduce process on those nodes. Okay, good. All right, now coming back to Sanjay's question, can you give an idea if a cluster has 4,000 plus nodes and name node comes up and contacts all the data nodes through heartbeat, how much time will it take? Okay. So if you have 4,000 plus node, that's actually a pretty big cluster. And and basically the connecting to all the data nodes through heartbeat is in parallel. Okay. So a heartbeat generally goes at 5 second per 5 seconds per one heartbeat per 5 seconds, and that means it might take maybe around. I I mean, it'll be difficult to say right now, but let's go by the probability. And considering all the failures and all of that, it might take up to maybe a minute or so. My approximate time would be maybe 2 minutes. Now, Anandita's question is, what is the application master and the container here in this question? So, MapReduce process would run inside MapReduce application master. Okay, the application master will launch the MapReduce mapper inside. So the resource manager would allocate one application. So resource manager will contact the node manager that here is the program which is called MapReduce, who wants to execute on each node, and node manager would create application master inside the inside the node manager would create application master for the MapReduce, and the okay, and the container will ensure that the MapReduce does not cross the boundaries which have been allocated to it. Okay, container, you can think of it like a policeman. All right, all right. Any more question, or should we move for next one? All right. Next question. Next conceptual question to you. Find the anagrams in Hughes text. An anagram is basically the different arrangement of letters in a word. The input is the cat act in tic-tac-toe. Can you just post your approach in the chat box? In the questions box, can you post your approach? Whatever you have written there. It'll be difficult for me to hunt down each one's answers. Okay, so this is on 29th August and session number 4. I hope the recording is going on. Yeah. So we have one or two answers. Okay, let me just put it. So this is Ravikant's answer. And he says that in the map will give out key, which is sorted word. Okay. And the value would be word itself. And reduce will group based on the sorted key. Okay. Yeah. So in the reduce, you will basically check if there are multiple instances and nothing. So grouping is already done by Hadoop for you. So you don't have to do the grouping. Okay. Brilliant. Brilliant, Ravikant. Right. Now there is another suggestion from Sandeep. List down words with weight by summing the letter of the word and the group using the weight. All right, I have a counter question to you, Sandeep. The question is, let's say you are saying list down words with weight by summing up the letter, right? So if you have AC and BB, as per your approach, they both will have the same value, isn't it? If you assign 1 to A and C to 3, so 1 plus 3 would be 4, right? And similarly, 2 plus 2 will be 4. Is that what you're saying? So that means these two will be grouped together. If your 4 is the key, because you are saying that please, we are going to keep, we are going to print the weight. Probably that's what you're saying, right? For each weight, you're grouping the words. All right. There is another approach we will have a look at. Good. Awesome. So Sravna's approach is similar to Ravikant's. And then we have Lakshman's approach, which is similar to Ravikant's. Good. Good. We have same approach from Anandita. For each word, sort the ascending order, print the key as original value, and sort it one. Brilliant. Brilliant. Anybody else? So here the idea is to bring all the anagrams together. An anagram is the arrangement of the letters in the word. Okay, all the different arrangements are there. Okay, so for example, the cat and tack and act are anagrams. They are different arrangement of the letters in the word. Therefore, they are anagrams. Okay, so yeah, so the approach is going to be this way. I think this will make more sense to you. I got couple of more approaches from different batches, but this one seems to be better amongst all. And if you have a better approach, please let me know. Okay, so what our mapper does is, our mapper's role, our overall way of looking at a problem is doing the group by. Okay, doing the group by. So when you think about the whole problem of MapReduce, you should think about how can you solve this problem by using a group by, or by using our sorting algorithms. How can you bring things together? What should be our key such that the things which we want to bring together should come together? What should be our key? Okay, so since an anagram is different arrangement of same letters, right? So if you order them, no matter in what arrangement are they, the after ordering the characters, the result will be the same. Therefore, all anagrams will have same string output if you sort their letters, right? And hence that could be a great key. So let's have a look at it. So for each word, so our map function is going to be called on each line in the text input. Therefore, it will first break down the line by words, and for each word, it will sort the letters. EHT will be the key, and the value, since at the end of day, we want original word. Okay, therefore, we put our original word in the value. So cat, if we sort it, A comes before C, comes before T, as per the dictionary, as per the alpha, we call it lexical sorting. So we after we arrange the letters of this word in alphabetic order, cat becomes act. Act is the key. Similarly, in case of ACT, the value is still ACT. And even for tech, the key is ACT because you know the reason. All right. So for TIC, if you arrange these, it'll be CIT because C is smaller than I, then smaller than T. And for TOE, it becomes EOT. All right. We are not reversing it. We are just arranging things in the letter. It just so happens that for if you arrange the, it becomes reverse of it. Similar is the case here. But okay, but that's not what we are doing. We are basically arranging things by the alphabetic. So Lloyd is saying that for each word in the input, print key which is sorted tuple of letters billion. That's what we are doing. So in the inside of our map function, we can do whatever we want. Okay, Sanjay, it's a answer to your question. So we can do inside a map function, we will be given only a record at a time. Okay, and inside map function, we can do we can do whatever we want, whatever we want. Okay, that means we can make a database call. We can even send an email inside map function. So if there are 1 million file in a text file and you are sending an email for each line, then there are going to be 1 million email that are going out. So you can imagine that if you had to send 1 billion email to people across the globe, you can use MapReduce process by putting these 1 billion emails in a text file and running the email mapper everywhere, right? So you can distributedly send an email 1 million emails by utilizing bigger set of network. If you have 4,000 nodes, you can force MapReduce to execute your program on 4,000 nodes and parallelly send the email to 1 billion people, right? Or if you are using you can even do a wget. Wget as in download a website or make a REST call. So you can do anything you want inside the map function because that's what the program is all about. All right. So here, when we are saying sort, okay, so we are basically sorting something like cat. We are saying sort my letters of the cat, which is for each word we are doing that. Sanjay, we are not sorting bigger text. But yeah, for doing a small string sort, you could use a counting sort. If you know clearly there are only 26 letters in a word, you can do a counting sort, which is far more faster on problems like this. Okay, so instead of using a standard sort process, I completely agree with you. The standard sort libraries might be little too expensive for the work. Therefore, you can write your own counting sort. if you are really aggressive with respect to optimization, that will be your next step for the optimization. If somebody asks you that how would you further make this algorithm faster, then you can say that I will write a better sort algorithm to do the to sort the letters, because sorting the letters is easier if you do the counting sort. Make sense, Sanjay, to you? Great. Okay. Counting sort is something like you basically count how many times A occurred, how many times B occurred, how many times C occurred, and then you keep a note of these, and then at the end of it you just print whatever you have encountered. All right. Now going ahead, so this is this clear to everyone, or you want me to go through the whole process here? Anyone? So we basically created the key by sorting the letters. And once that is done, this line, do you see this line? From here to here, the big line. This is the work done by Hadoop. From here to here, till here. This is done by Hadoop for you. Okay, let me note it down here. So from here to here, uh, these three things till here is done by Hadoop for you. The data given out by mapper gathered by Hadoop as in MapReduce process, and after that the result is sorted, grouped, and then given to the reducer one key value tuple together. Key and the values for each key the reducer will be called. All right, should we move ahead? All right, brilliant set of questions today. And okay, so who did this problem? Anybody? I see that you have done it, but right now pulling it out, it will be difficult. Output order does not matter much, Savna, as long as we are achieving the problem. Output order would not matter. All right, let me just go through your questions again. So Ravikant is saying, let map be the key. Okay, the key will be user ID and value will be DNA. No, but we want to find out, we want to bring all the users together for each DNA. So if you put the key as user ID, what would happen is the in grouping for each user ID, if there are multiple DNAs, they will come together, not the other way around. Okay, so again, let me again clear this doubt here. So the grouping is not being done by your reduce function. Okay, grouping is not done by reduce function. Grouping is done by Hadoop. And when you say group it based on DNA sequence, that that's exactly what do you mean by putting the key. So when you want to say group based on DNA sequence, then you put key as DNA sequence, because that's the basis on which Hadoop will group your data. Okay? So when you want to say group my data based on DNA sequence, your mapper will dictate that part. Your mapper will dictate that part by saying that my grouping key is DNA sequence. Okay? So when mapper gives out key and the value, it essentially says, please group my output by this particular key. All right? All right, brilliant, brilliant. So I think everybody got this. So Sandeep Mane is saying that, do I need mapper? Reducer will have to just average average out based on user one, user two. So I mean, reducer will do nothing but find the unique values. That's all. Okay. But yeah, mapper has to give out key and the value. Okay. All right. Again. So it's basically for our mapper function, we do not have access to anything. So when we say map input, inside map input, this is from Anandita. For each DNA, check whether it's the same or not. Print the key. Same with what? So are you saying that inside our map we will pick up one and then compare with the rest of it? Because for a mapper, it will be only one record at a time which will be available. Mapper, your map function will not have access to any other record. All right. So basically, it's a classic group by. Okay, it's a classic group by. If you have to do it using SQL, you will say select DNA, concat users from my table, group by DNA. And whenever you look at this kind of syntax, you should get the hint that, okay, if I have to write MapReduce here, the key is going to be the same as what we are trying to group by on. All right. So yeah, it's pretty straightforward. Key is DNA and value is the user. And in reducer, you just print out the distinct users. Okay. Everybody okay with this approach? You want me to explain further? Or should I move on to the next problem? Because the next after this, the third B is probably the most difficult part out of all. All right, I think everybody is clear. All right. So whenever we have input, so this data needs to be grouped by DNA, which is the second column. Now, whenever we want to, so the overall objective of MapReduce paradigm is being able to group data with some key, right? And what is that key? That key is given out by the map function. Okay, so our map function decides what is the key and what is the value. Okay, and whatever is the output of the map function is taken by the Hadoop, and based on the key the data gets sorted and grouped. And once that grouping happens for each group, our reduce function is called. All right. Therefore, if we just straight away make the key as ACGT and the value as user one, then ACGT and here, if you look at this way, if I'll show you quickly. Okay, so after, let me just clean it up. Let me just clean it up. All right. All right, this is something, these kind of cleanup happens inside the mapper. What am I doing manually? So each line will be fed to your mapper, and what mapper will do is just give the key and the value. All right. So what mapper will do for each of the record, it will find out, it will split it by space. Okay, and then it'll say like this. Okay. So DNA will become the key and the value will be the user, and then it'll get sorted. Okay, you can see that just because of sorting, these two have come together, right? And these two have come together, right? And these are not together. Make sense to you now? So in so Hadoop will do all of this sorting and grouping for you. Okay, so Hadoop, you can always think of Hadoop's key value like a big grand, you can think of it as a big grand group by. Now you can see that user 1 and user 4 have come together. Prabhat, is that clear to you? Great. Brilliant. Now let's move on. All right. All right. Now let's go on to third B. All right. How many of you have done this particular problem? Could you just paste your answers? And yes, Lakshman, that's correct. All right. All right, brilliant. So please paste your approach and let's take a break till then and come back. Should we take a break of 10 minutes or 15 minutes? 10 is fine, right? All right, let's take a break for 10 minutes. Back by IST. All right, should we start now? Great, great. I think almost all of us, all of you are back. Great. So now these are good answers. These are good answers. Let me go through some of them quickly. Okay. The answers are here. Let me just try to paste it here. It'll be difficult for me to read so much. I don't know if I can introduce a new column and make it. Of course, you can introduce a new column and make it a key. Even if you want to do anything, you can put that as a key. Okay. There's no hard and fast rule on what can be the key. Okay. All right. This is also good. This is also good. All right. So what Vidya has done is she has created a composite key of DNA and reverse DNA. Okay. So if you had to just imagine that there is no, let's try to deal with the deal with in the form of strings, right? Plain text strings. So what you have done is you have put key and dollar dollar reverse key. I'm putting dollar as the separator here, or maybe dash. Okay, key and the reverse key. That's what you have done. So have you put something like key and its reverse key, or is there some reason based on which one should be first and which one should be second? All right. Let me just leave your answer and then we will talk about it. All right. Now, second is this is Vedya. Then there is Lloyd's answer. Good. So, all right. This is something which you need to think about. So, what he's saying, this is Lloyd's answer, and this is Vedya. All right. Lloyd is saying that these are very important questions, and these things you invariably you will come up with these approaches, and that's why I want to go through the distinct approaches from all of you. Okay. So Lloyd's answer is that function map input, and what he's doing is for each user in the input. Okay, what he's doing is he's printing the DNA and the user first, meaning he's printing two key values. That's perfectly normal, as in one map function can print as many key value as it want. Okay, that also means that in case there is a bug in your program and your program is running infinitely, your mapper function can actually overload the framework. Okay, so your mapper function can print out as many keyval as it wants. All right. And it actually happened recently. So one of the users was trying to do that, but good part is the MapReduce framework kills it after a certain time. Coming to the problem again. Okay, so for each input, this is what it looks like. For each input, he's printing two key value pairs. One is with the DNA, other is reverse DNA. Good. So which means there are going to be two for each. You can see that. Reverse as in reverse from it's reading from the backside. Good. Now Hadoop will return you ACG good user 3 and user 5 and GCA user 3 and user 5. All right. In the DNA in here, okay, So you are returning user array. Now the problem here is you will get two sets of both. See that? You will get two sets of both. That's the only problem you will have. Correct? And to eliminate that, you will need a second round of work. Yeah. And to dedupe, again, you will have to create a MapReduce process in which the key will be this and value will be nothing. Value may be one or null or whatever you want to do. And then again, the second MapReduce phase will be there. Correct? Good. Good. This is also a good approach, just that it needs multiple phases in order to dedupe. Okay, you will need one more MapReduce phase to deduplicate. And what do we mean by multiple MapReduce phase? You can actually store this data. This data will go into HDFS. Now a fresh MapReduce will read the data from the HDFS and do the process and put it back into HDFS again. So you can have as many MapReduce chain as you want. Good. Now coming back to your questions, I missed Lakshman's because that was more the first one. All right, this is from Laksh, and key is POSO with both DNA sequences as variables with equals and comparable compared to, as you said. Yeah. So if you do that, I think that makes it a little complex. And to keep everything in perspective, let's try to do it using strings. Okay, because I mean that wouldn't solve it. Even if you implement equals and compare to, it will be difficult to implement, because if you look at the implementation detail of compare to, that will be far more interesting thing to do. Okay, so to keep it simple, we will try to think in terms of string or numbers. All right, good, good. Okay, there is another good approach. Let me have a look. Let me see if I think a better idea would be to all of you to also go through it with me and then pinpoint the errors. Okay, that'll be interesting. So here you can see that this is from Ravikant. Ravikant says that the mapper function will give out key as sorted DNA sequence, then comma, then DNA sequence. So what he's saying that it's a composition of this. So on what basis your key should be sorted? So okay, so in reduce function, let me just see that should be based on DNA sequence and then group based on the second set of keys where we have an array. In this array, we can hack. All right. I think I'm getting where what do you mean? So what he's saying for ACGT, okay. So what he's saying that the first, all right. Here you have done a little bit cleverness. The word hack need to be further analyzed. Okay, it needs to be further analyzed because that actually cleverly hides the actual work that needs here. Okay, this is another approach. Mm-hmm. Mm-hmm. All right. All right. This is also an interesting approach. So what he's doing is he is saying there are two approaches which he has given. First one, somehow I'm not very convinced. Second approach is interesting. What he's saying is let's use let's use let's first bring all the users where DNA is an anagram of each other. Okay? Which means ACGT and TGCA user 1, user 4, and user 6 and user 2 will come together. And then in the next round, in the group by, he will compare these values and give out the results. Interesting, interesting. So what he's doing is first group every all of these things based on the like an anagram. Okay, so ACGT, TGCA, ACGT, and AGCT, all of these are anagram of each other, right? So user 1, user 2, user 4, user 6 is bringing together and then ungrouping them by comparing whether they are mirror image or not. Interesting, but little inefficient. All right, good. All right. Vidya is saying, okay, okay, all right, all right, and yeah. So further to Vidya's approach, which is there, what she's doing is user one becomes group one, AGCT. Yeah, there is little inefficiency involved, so we'll go into that detail. All right. Lloyd is saying we cannot use list as key. We can use list as key, but we'll have to implement the compare to, and we'll go into the detail of that one as well. All right. This is interesting. Interesting. Okay. The Rajesh's approach is something you can tell me what's wrong with that. All right. You can also evaluate this. Anybody? I will concatenate DNA and reverse DNA and sort the resulting string in. Okay. So he's saying that he has got understood what is wrong with it, but actually you are very close. You are very close. All right, great set of answers. All right, so okay, okay, so all right, looks very interesting approach. And Vidya, I'll go through your approach. I think I'm getting what exactly you mean. All right, and the approach is actually correct. All right, now here is probably some of you have got it right. Here is one of the approach. So I'm doing something a little clever thing here. I'm picking up the smaller of the reverse and the DNA. So I'm picking up only the smaller one. Or the way Rajesh was saying, you could also form form by concatenating, concatenate the DNA and reverse of DNA, just that, just that in an order. Okay. So how should I, let me put it this way. Let's say a, so either you concatenate or you just pick up the smaller one. Okay, the result will be the same. Let's take a case for ACGT, the reverse is TGCA. I'm saying that I'm just going to pick up the smaller one out of the two, and the smaller one is ACGT, right? A is smaller than T, and therefore ACGT is smaller. Or you can pick the bigger one, or you can simply order the two, as in arrange the two in ascending or descending order, and concatenate them. The idea is, no matter what you do with this, the the people who have the DNA and the reverse of people who belong to the same family should come together. Now, either you pick the smaller of the DNA or the bigger of the DNA out of DNA and its reverse image, okay, we will get to the same point. You can see that. So user 1, you can see ACGT, and user 2 both belong together, right? So if you reverse ACGT, which is TGCA, and pick up the smaller one, ACGT, now in the second case, the smaller of TGCA and the reverse of TGCA is ACGT. So the smaller of TGCA and ACGT is ACGT, right? Therefore, in this case also, the key would be ACGT, all right? So basically, the idea is to figure out what could be our key, so that the users who are either the mirror image, users who have the DNA mirror image or the same, should come together, right? So are you able to get where I'm getting to? Do you have any questions on this? Everyone? Rajesh, Ravna, Vidya, Ravikant, Lloyd, Michael, Shavana? Great. Himanshu, David, Anuj, Anandita, Jairam, Joshi, Kanaga, Karthik, Lakshmanan, Mike, Nandini, Priyabrat, Richard, Sandeep, Sanjay, Suresh, Tushar. So smaller is just picking up the smaller out of two. Smaller as in, if you have to put them in dictionary, which one will come first? Right. So you can have a look at here. Smaller is something like, I'll put it this way. Is like a dictionary. In a dictionary, cat is smaller than the rat. That's the only place cat is smaller than the rat. Okay. And cat is also smaller than the kate, right? All right. Good. So there is some question. All right. So for ACGT, let me see. What does it mean? All right. This is the answer from. Yeah, you're right. Yes, you're right. This is correct, Shravran. Good. So alphabetically, Michael, if you place them in the dictionary, so cat will be before the rat in the lexical order. Yes, that's correct, Michael. All right. Now, now there is a question from Rajesh. What about the key if I want to concatenate DNA as the key? What about, you mean the value or the key? Okay, okay. So he meant to say if we are concatenating, okay. So right now let's just assume that we are concatenating by putting the keys back to back and putting them as, with a separator. Maybe space could be a good separator. Okay, space could be a good separator. So any string can be the key. Okay. We will talk about the concatenation in terms of objects later on when we talk about Java. Right now, you can just assume that you are concatenating DNA and the reverse of DNA in the form of strings, and that's all. All right. Great. So, should we move to the next one, or is there any question at this place at this point? All right. So here is a good question from Sanjay Tandon. Sanjay's question is, can MapReduce also solve database SQL-like problem which run into multiple pages like select XYZ from table A union select ABG from table B? The quick answer is yes, and they with sort of a disclaimer saying almost. Okay, as we go forward, when we talk about big hive, this question will get answered slowly. It's a tough question to get answered. So almost is the political way of saying yes, it could be done. Almost every SQL query could be translated into MapReduce. That's why project like Pig and project like Hive exist. Okay. And similarly, project like Spark SQL, which has come recently, they exist because it is almost possible to solve using SQL. Okay. Now, the reason the keyword called almost here is the reason why we still have to learn it, because we will have to understand where is the catch. Otherwise, we could have just said that there is no point in learning MapReduce. Just start using SQL and you'll be happy. There's no point in getting into these internals. The reason is the game is almost the game of big data is about the optimization. And unless we understand what we are doing just right now, unless we understand the MapReduce and the mechanism under the hood, we won't be able to write effective SQL queries on top of Hadoop. Okay, so Sanjay, was I able to answer the question? Good, good, brilliant question, and I'm happy that you are beginning to think that way. All right. Okay, so should we move to the next problem? All right. I'm assuming it to be yes. All right. Who solved this one? Okay. Could you just paste it? Yeah. It'll be easy for me. Me asking to copy paste you is similar to name node delegating work to the data node so that he doesn't have to do things on behalf of everyone. All right. So Shravnan was saying I could able to bring output using two mappers. Good, good. That's how it has to be. So it can be solved using multiple mappers, multiple MapReduce phases. All right, good. Let me have a look at. Looks like Lloyd has done it. So here is Lloyd's approach. So here is the, okay, good. So, all right, all right. So for each line in the list one, so if you remember the problem is to basically join the two list. Okay, good. So for each line in list one, prepare this. Brilliant. For each line in list two, prepare this. Good. And then, all right, for each key in the dictionary, we do this. Okay, so let me put it this way. What you're exactly, so here is what you're trying to do. So first you cleaned up the list one, then you cleaned up list two, you got these two lists. Okay, then for next map reduce, you just concatenated. Concatenate means the output is a list of files always, so you can put dictionary 1, dictionary 2 in a single folder and give to your MapReduce phase, next MapReduce phase. Okay, and yeah, inside that map function, you can simply say that this is the result. Okay, and after this, uh, so this is the second phase. So map will do this, and it will return something like this. Okay, okay, good, good. You're almost there, almost there. Yes, there is one step that you have skipped here. So basically here that lookup is not that easy. Okay, because these two lists, they are huge, so you cannot say for each value in dictionary 1 look up in dictionary 2, right? Instead of that, we will join dictionary 1 and dictionary 2 such that for for each key the values come together. Okay, good. Sandeep's point is that we could simply do select uh, person comma sum from join list 1 and list 2 on basis of this. That's exactly we are trying to do. Although it seems like a simple join problem, after joining we have to just group the data and get the result. Okay, all right, I think Vidya also has done really well. Good, good. So here is Vidya's answer. Yeah, just that the data, as we all know, that the text file actually corrupts the data mostly. Let me try to increase that. Yeah, this looks better. It's a tab size here, probably that's the only problem. All right, let's try to decipher it. So for each list, okay, so print voter, 40, and worth. Now this is the problem. Here, the problem is that if you think about in terms of map reduce, and each voter is being fed to the mapper, and we are finding the worth from the list too, then what would happen, then each mapper making a call to another machine and trying to do that, they'll be horribly slow. Okay, so this will be horribly slow because for each voter in list 1, if you're making a call to the second list, and this second list is not in the memory, it's also bigger list, so you cannot load that in memory. Okay, so here is the trick question. Yes, so the Michael says the replace voter with the worth. That's exactly the problem. Main problem is the way we have been thinking is pick one value from one, look up in second. That's not how you can solve the big data problem. Look up, when we say look up, it's actually a difficult problem. If you think in terms of 10, say few gigabytes data, or few maybe 20 gigabytes of data, it's actually difficult to look up in that data. The only way to solve these kind of problem is by using some variation of sorting algorithm. If we have to join two data sets together on the basis of certain field, you basically create the MapReduce output in such a way that the key on which we are trying to look up, okay, the basis on which we are trying to look up, based on that we bring those records together by making that key as the key for the map, so that when the data gets sorted based on the key, those records which we are trying to bring together, they come together. So we are trying to exploit the sorting nature of MapReduce in order to do the lookup. All right, good. I think yes. So Shabna has got the correct one. Probably I'll describe that next. Good. Brilliant. Brilliant, Shabna. All right. All right. Let me describe it in detail. All right. This is something you have to think about, and they are all part of joins. We will also discuss join, join again. Okay. We'll also discuss the map side join, reduce side joins, and those things again. All right. Here is the idea. All right. The way. The way Lloyd was cleaning up the data, let's say we have cleaned up the data such that list 1 and list 2 has key and value listed together. Now, in the mapper, all we did was whatever is the result, we read both the files list 1 and list 2, and all we do is print out key value, meaning from both the sides A5, B1, C11, D12, and then AC, AB, BC, CF, and FC. So we basically, in the mapper, we did nothing. We just printed key and value from both the files, because for mapper is getting the data from both the files together. As I was telling you the other day, that when we are feeding to the mapper, we can feed either the individual file or the full folder or a list of files. Okay, so whenever we give the list of files to the mapper, it behaves as if all those files have been concatenated and given the input. Now once that happens, so Hadoop will bring this data together irrespective of their data types. Right now, it's just considering everything as numeric. So here, A5BC will come together, B1C will come together, and so on. Okay, let's try to interpret what does it mean. It means A has voted to B and C. So what does list 1 contains? List 1 contains who voted for who. Here it says A has voted for C, A has voted for B, B has voted for C, and C has voted for F, and F has voted for C. And list 2 contains what is the worth of individual person, right? And our objective is to find out the total vote count of individual person. So C has been voted by A and F and B, right? C has been voted by A, B, and F, right? Now F does not have any worth listed here, so we are assuming the worth of F as 0. The worth of B is 1 and worth of A is 5. Therefore, the total vote count of C is 6. Now B has been voted only by A. Therefore, B's worth is only 5 because A's worth is 5. So the total vote count is summation of all the voters of a votee. Summation of the worth of all the voters of a votee. Now, now in the mapper, the two lists got concatenated and Hadoop sorted it and grouped them together like this. And this tuple looks like A has voted to B and C, and A has got a worth of 5. Okay. Now, if you look at from B's perspective, B has been voted by somebody whose worth was 5. C has been voted by somebody whose worth was 5. So C will gain 5 because of this voting. C will gain 1 because of this voting. B will get 5 because of the voting due to this particular voting, and so on. Now, what we do in the reduce is for each key we will basically print out how much each one is getting vote due to this. So B got 5, C got 5, and again when the next reduce call happens, then it will. So this is a second reduce call, just to keep it very clear to everyone. Okay, and then this is a third reduce call. All right, you can see that. So B got 5, C got 5, and C got 1, and F got 11. Now, now the next phase, from here you see the dash line, from here the next phase is starting. And again, key remains this one, value remains this one, and Hadoop will group it And in the reduce, we basically sum up these values. Sounds good to you? From reaching from here to here is very simple. It's basically standard group by. Okay, you have to just sum up all the values C has gained and B has gained and F has gained. Does it make sense to you? All right, all right. Now Shravna's question is, output also contains A equals 0. Can anybody tell me that? As per the problem statement, we wanted 0 as well. Can anybody help me with that? Yeah? We wanted A. Okay, let me just modify the problem here. So we want A at 0 as well A, B, C, and yeah, that's it. Yeah. So who can help me with this? Yes. So we want A0 as well in the output. You see, this was the problem. You see, A0. So what tweak would you like to make in this? Okay. So Lloyd's point is, can I populate list of distinct user and later find the missing users? Yes, that is one approach, but it's far easier than that, Lloyd. Yeah. Okay, okay, this is also good. So Lakshman is saying that during reduce, if the key has no vote, put 0. Brilliant. That's one approach. And all right. Actually, the kind of approach which I thought is better is, while during reduce, when we are awarding B as 5, C as 5, we also award A at 0. A at 0. Okay. Similarly, here B is voting somebody. So B gets nothing out of this transaction. So we put 0 here. B0. And similarly, the next one is D0 and so on. See that? Yes, we can also award all the voters with 0. That's also good idea. Thank you, Vidya. All right. So it's not that difficult. You can do that. All right, no problem. Lloyd's question is, where did this D12 came from? Okay. The All right, this was something which I did. You can see. So there is one guy called D whose worth is given to us, but he has neither been a voter nor been votee. I have put this specifically purposefully. Okay. In the same way, there is F who is a voter, but his worth is not available to us. These are the corner cases you need to worry about. So, in the reduce phase here, you have to take care of such cases. All right. It essentially means, so when I was putting A0 here, so similarly, you can do the other tweaks. In case there is nobody here, just ignore that row. In case there is no value available for something, just ignore that row. consider that these two as corrupted data and so on. Okay. Now, when I say A0 here, it does not mean, yeah, it means that A got no votes, no value out of voting for anybody. All right. All right. So, do you know that this voting algorithm, what we are talking about, is modeled on a very important problem? This particular problem, problem number 4, has been modeled on a very important problem. Probably the reason why MapReduce was invented in the first place. Anyone? Yeah. So, does any important problem comes to your mind when you look at this voting algorithm? Sanjay says graph network. You are there. Yes. Something which, I mean, yes, it is to do with graph network, but because of this, probably, probably the one of the large company which is existing today is actually existing because they solved this kind of a problem. Yes, Anuj, that's correct. The Google PageRank algorithm is what it is modeled against. Okay, all right. So yeah, so basically the MapReduce itself was first used to compute the Google's PageRank, and that PageRank algorithm is very similar to this voting. Just that in their voting, the worth, this worth which we have computed, was being used again and again in order to keep on updating their worth. So the worth which was in the bank account is in case of PageRank algorithm is same here. All right. Those who do not know that, I'll just repeat it. So in case of Google's PageRank algorithm, it means that if one page is linking another page, this page is voting to somebody. Okay. So if my page is linking, giving a href to your page, I am kind of a voting for you, and my vote is equal to the worth I have. If more pages are voting for me, my worth keeps on increasing, and in case I vote for somebody else, they get far more one. Okay. So basically the pages who are being at linked by most important pages, their value keeps on increasing. All right. Is that clear to everyone? Yes. So PageRank was computed in the same manner. Yes, Suresh, that's why the link building actually start. All right. Sanjay's question is, I could not follow why A got 0 votes. Okay. So A has not been voted by anybody, right? So effectively A has got 0 votes, right? But if we have to display explicitly, if you have to display explicitly that A has got 0 votes, then what you have to do is you have to uh, devise a little tricky thing, as in you have to, for each of the this row, the way we are printing B got 5, C got 5, we could say the voter who is voting got nothing because of voting somebody else. Okay. In case of page rank, the page actually gets negative votes. Their value decreases if they vote for somebody. If I'm linking to your page, my worth actually decreases. No. So A is the voter and C is the votee, means C has got A's vote. Okay, Sanjay? And B has got A's vote. A has not been voted by anybody. Good, good. Any questions on this algorithm? Anybody? Yes, this was a little tricky one. Yeah. So good, good. If you got it, then it is good. If not, then I can explain again. Basically, it is simply a matter of multiple map reduce phases. Yeah, great, great. So Lloyd got it, Michael got it, and all right. So hi, is everybody with me, or have I lost you? Okay, Anuj is with me, Sravnan is okay, Ravikant is okay, Suresh. Everybody else? So I've got only confirmation from 5 people, 6 people. Yes. In cases like this, where Hadoop executes the job, so Lakshman's question is, in cases like this, where Hadoop executes the job, same it executes on the various nodes. Okay. Yes. Blocks may be distributed across multiple datasets. We will talk about this again. So your question is, your block may be distributed across multiple data nodes. Then how does it basically handle those kind of problems? So that we will discuss now after this. All right, good question. Good question. Let me explain, Priyabrat. Reduce part here. Basically, in case of mapper, we took converted the key as the voter. Worth and the votee remain in the value. Worth and the voter came together like this. 5 BC. So worth and the voter are in the same group, same in the values. And then in this reduce phase, so what does reduce phase get? Reduce phase get key and all the values together. So your reduce function get two argument. First argument is the key, and the second argument is the array of values. Okay, that's what your reduce argument get. Now this reduce, for each of the values, first it will find out which one is the number, and and for rest of it, for the rest of it, it will generate the key value pairs. Reduce is generating key value pairs, note that, so that the next phase can pick it up without needing the mapper. All right. Or you could just do nothing here and leave it to the mapper of the next phase to generate this kind of key values. All right. And how are we generating? We are saying, because of this B's worth has been increased by 5. Why? Because A has voted B and A's worth is 5. So B's worth has increased by 5, C's worth has increased 5, and so on. And after that, in the next phase, simple group by the votee, we just sum up the values. Okay? So that's what it is. Is that clear, Priyabrat, now? Awesome. Great. Let me move ahead and then we will discuss further problems. All right. Now let's try to do some nice execution, and let's try to today's time. Now we discuss the problems. Okay. We have good discussion on the problems. We will try to do the streaming job, and then we will talk about the limitations of MapReduce, and then how do we test, and then the further assignment. All right, let's see what all we can complete. Nothing to worry. That doesn't mean that we will rush into it. We will just try to focus on each individual concept, because these are very important concept. In case we miss something, it is I mean, although we'll be able to continue, but still uh, it's something which we should not miss. Although if you do not get MapReduce, you can still understand Pig and Hive and all of the rest of the technology. But MapReduce is a very important idea in case of distributed computing. It's not only useful in case of Hadoop, but it's also useful in case of Spark. The future technologies are very much dependent on the previous technologies, which are like MapReduce. All right. And all of us should understand that it takes some time to actually get into that mindset that okay, we can solve most of the problems using MapReduce. All right, so nothing to panic. All right, now let's try to understand the most simple way of executing map and reduce. Okay, so the most simple way of executing map and reduce is using something called streaming job. Okay, streaming job is a Hadoop library which makes it possible to use any binary as mapper or reducer. Okay, mapper gives out the key space key tab value per line. Reducer gets ungrouped data. Please note this point, that reducer gets ungrouped data. Unlike what we have learned so far, that reducer would get grouped data. Here, just in the case of streaming job, which is a form of MapReduce, internally it calls the standard Java MapReduce. Yeah, but it's simpler to execute and simpler to explain right now. All right. So again, let's have a look at what we are trying to do. Okay. So in case of streaming job, the mapper gives out key tab value one per line, one key value pair per line it will print. Okay. And reducer get only the sorted data. If it wants to group, it can group by itself. Now let's take a look at what we are trying to do here. Okay. Now, if you remember Let me try to paste it here. Yeah. So this command is, we are saying Hadoop. The instead of saying fs, which was for HDFS, we are saying jar. We are providing some library. .jar in case of Java is a bundle of programs. Okay, it's generally a library containing many classes. Each class is something which can be used to do something. Okay, so Hadoop streaming.jar basically contains the compiled code which is running Hadoop streaming. Okay, in case of if you are coding in Java, instead of using Hadoop streaming.jar, you will be using your own jar. Okay, that we will discuss after this. So right now we are using Hadoop streaming, which is pre-built MapReduce library. And what does this do? It basically let you use any program as mapper and any program as reducer, as long as these programs, whatever we are using in as a mapper, these program, as long as they can be executed on each machine, as and they are giving the key and the value, and accepting the key and the value from the screen. Okay, so a mapper needs to give out key and the value, and mapper should be able to run on any of the date, any of the node on the cluster. It should not be that you are putting some command in mapper which is not existing on those nodes. All right, we will talk about how to get that done also, but right now let's understand it. Map, whatever command you give in the mapper, it is going to get executed on each node in the on each node where this file is existing. Okay, so mapper, the same philosophy which we had learned just before this. Okay, so we are saying that here is my input file or input folder, and create the output folder here. This is my mapper command, and what does it do? It basically splits the input data into one word per line. Now you might say that I just explained that the mapper is supposed to give key tab value. In case there is no tab, it thinks that the value is null, which is completely okay. All right. So I just told you that. So in case there is no tab, it will consider key and the value as single key. Okay, if there is something like this. If there is multiple tabs, okay, if there is no tab, that means value becomes null. If there are multiple tabs, then the second tab is part of the value. So mapper gives out key and the value. All right. Now, what is our mapper doing here? Is basically whatever is the input file given to the mapper, it's replacing space in that with new line. And remember that mapper was getting one line at a time as input. Similarly, our SCD will get one line at a time as input, and it will replace space with new line. Okay, G/G means it will replace all the occurrence of space in this particular line. It will replace with new line. Okay, so if it has multiple tabs, then that second tab will go into the value. All right, Shravana. Yeah. Now reducer, what is it doing is it's basically whatever the result comes in from the Hadoop after sorting the output of the mapper, it will create, it will pass that result through this command. All right, let's try to execute it. Let's log in into my courses. Let's log in into the, I will, okay, so there, where is the Hadoop? 10th October, 29th August, 7. So yeah, this is our class. Okay, so let's just open the console and copy the password. Student 17. Sorry, Hadoop 17. Hadoop 17. Thank you. Yeah, thank you, Sharna. And here is something. Let me fill with my local folder instead of bothering yours. Yeah, here is our big.txt, and let me just see if it exists already somewhere. I had put in the data mr word count, so I think I have put it there. Yes, it is there. You can see that. And inside input, there should be one. Yep, there is one. I can delete this particular file easily. We can delete it later, never mind. So now what we are saying is, let's just copy this particular folder's name and keep it here. So instead of that, we can say, yeah. All right. Now output, I just want to keep it in my own folder. Let me just put it like this. Okay. All right, we are all set. Let's start. Let me clean it up. We'll have to convert this multiple lines into single line because that's how it wants. Either we could just put slash here like this, like this. Okay, if your program is, if your script is extending to multiple files, this is what you could do. Multiple lines, if your command is going to multiple lines, this is what you do. All right. Now there are a few things happening here. One is that the process has started and it has basically given us a URL to track. Okay. It will show us. Okay. What shortcut are you using to copy to Veti? I'm basically copying it using. I'm basically copying the password using this. Okay, you mean to say doing copy paste from my terminal? So Laksh is asking that what shortcut are you using for copying? Actually, for those who are from Windows, it becomes difficult to copy paste. Because I'm in Linux, I'm able to copy paste. I'm I'm not sure how does it work generally. So let me say Control C. So try Control C, Control V. I don't know. This is something I've not tried. Alright, so right now we have not created any jar file. We are using the jar file of Hadoop streaming, which comes along with the Hadoop installation. Alright, okay. Looks like most of you are facing a problem with respect to the copy pasting. So let me find out and then I'll let you know. Shabna is saying that Shift Control V is working. You can try that. Or Sandeep is saying that if you're using Chrome, then use Chrome's copy paste menu from here. I think, yeah, okay. All right, good. Good that we are seeing these problems. Okay, let me also go back and find out. Or maybe we'll see if we can enable the right click menu here. If you could enable right click menu, it will be actually great. All right. So here the result was there. Yeah, it has. So it has finished the work and also given you the complete statistics on what has happened inside it. Right now, it did two map tasks and one reduce tasks. Okay, so here is the details. Okay, nothing has failed, everything is successfully completed. And in case you want to get into what happened in case of map, you can see that there are two tasks executed. Okay, so it internally decides upon number of tasks it want to create. Can see the result. This one has executed on Hadoop 2, though we were on Hadoop 3. The result, it was actually executed on Hadoop 2. And here is what has happened inside the task. And if you go into this one is also executing on Hadoop 2. Okay, so there are two tasks created on each node, same node, for getting this executed. All right, now you can see that it has done a lot of work. Good, good. So let's have a look at the output as well. What's going on here? Okay. So what we can do is we can go into Hue, or we can just simply see our data. What was our data? It's in Asgiri word count. Here it is. So you can see this is where we have kept it. So either we can say Hadoop fs minus ls. This is our folder. This is, since it's not starting with a slash, that means the root folder, it's a relative path. All right, so you can say Hadoop fs minus cat, and we can put more. Now you can see that there's a lot more things that should be done, because if you see there is double quote here, then hash is there. We need to remove these all special characters and clean up the data, right? Although it has done the computation, you can see this do has come 80 times and don't has come 53 times, right? All right. Now, in order to improve this, we might, okay. So again, let's try to show you what exactly is happening. For each line in the input, let's have a look at the input file also. Let's try to have a look at the input file as well. So here, the data is lying at the root folder, and in the data, there is MR, there is word count, there is input, and there is this big.txt. Now you can see it is basically a big text file having some of the novels of Sherlock Holmes. It's a plain text file containing I think these many novels. Okay, right? And in the last, there are some other random babble which I have put into this, some text just to do the computation. All right. Okay. So this is our text file. So in the streaming job, this text input line by line is given to our SED. SED is search and replace kind of functionality. So SED for each line SED is called. And against each line, it basically converts each line into one word per line. And this dash line you see here, this is the job of Hadoop. All it's doing is sorting it and creating this list of words which are ordered. Okay, so you can see that Ga has come first, Ray has come second, and then Sa. And after that, this result as a whole is being passed to our command called unique minus C. Okay, that's what is happening. Unique minus C. What does unique minus C do? So if we had echo X new line or echo X semicolon echo Y, it is like this. If we give it to unique, it will basically give number of times things have occurred in an ordered output. You can see 2 has come now. Okay, so unique basically converts it. So is 1, rate 1, and Sa has come twice. Alright, now if there are multiple reducers, so what happens is some of the words would go to one reducer, some go to another, some go to another. Just that one key does not go to two reducers. It goes to one reducer. It became all the keys, um, all the all the values for the same key remains together. It would never happen Sa goes here as well as Sa goes here. No, it will always be together. Otherwise, the purpose of grouping will get defeated. Purpose of sorting will get defeated. All right. So Sandeep's point is why my command doesn't work in the same way. Just send me your command. Okay. All right, he got it. No problem. Good. I'm very happy that I delayed your response. You found it by yourself. All right. Now, what is a streaming job in context of Hadoop? Basically, in context of Hadoop, what is a streaming job? A streaming job is just a utility provided. Basically, somebody thought that not everybody is a Java programmer. So somebody from Hadoop's team thought, okay, not everybody is a Java programmer. So lots of people would be there who would not like to write Java code to get your things done. So what he did was he wrote a very general purpose Java program which executes external programs as mapper and reducer. So this Java program you see here is executing our the commands which we provided in the command line as mapper and reducer. Instead of you having to write all of this mapper reducer code, you're basically just surviving with couple of commands. Okay. All right, let me try to show you what exactly is going on, Shravana. Will that be okay? Let me try to just take this page. All right, let me just try to take this text. So what exactly is happening inside it? Let's say this is the text. Now, for each of this, we are going to execute sed. Okay, substitute substitute space with new line, and okay, what happened? That's not a great idea. Let me try to show you here on the command line. That'll be easier for all of you. Okay, let me just say big, okay, txt1 and paste it here. And let's say txt1. You can see txt1. Good. Now what's happening is we are passing the each of this line onto our command, which was /n, like this. You can see that it got suddenly converted into one word per line. See that? And then Hadoop is internally, this sorting, instead of we doing it, Hadoop is doing it internally. And now what is the result? See the result? And again, then our reducer, which is unique minus C, is happening like this. All right, you can see space has come 7 times, about has come 3 times, and has come 4 times, and so on. If you want to do, you can do a further sort, but yeah, that's just for demo purposes. So the has come 8 times. Shavna, does that answer your question? All right, all right. Now, if you have to improve this program a little bit, what are the things you would like to do? Anybody? Were you happy with the result which we got just now? So the result we got was looking little ugly. So let me try to go back to a folder, home folder, home folder, and there was Asgiri, not this one. Let me just sort it by the date. That's better. Okay. So also note that there are two kinds of file. One is underscore success. It's just an empty file which remarks that this process has finished working. And then if there are more reducers, there will be more parts. Okay, we'll show you how to run multiple reducers. So what are the things you would, how are the thing, what are the things you would like to do in order to improve this result? Do you see something wrong with this? Clean up the data, remove the special character. Thank you, Richard. What else? Suresh says that remove dot dot. Yeah. Sort by count descending. Okay, that we will do later. Okay, that's interesting. Replace non-alphanumeric character. Brilliant. So yes, let's just try to clean it up. Okay. So cleaning will happen. Do you want to do cleaning where? In the mapper or the reducer? Yes. So cleaning will happen in the mapper. That's correct. Because by the time we reach reducer, we have already grouped the data. So that's not a great idea. All right, because what's happening is in case of come and capital and small also is a problem, so we like to do couple of things. Let's have a look at the next script. Okay, so where is the next script? Yeah, here. Now let's try to create our own program. Right now we are doing it in shell. Tomorrow you might like to do it in Perl, Python, or any other programming language. You can do it easily. So let's try to create another program. What is this program doing? First, it's replacing anything which is any number of spaces or tabs with new line. Then it's removing all non-alphanumeric characters. and then converting everything into the lowercase. You can try executing these commands individually and test it. Okay, so what we are trying to do is we are basically creating all right, let's try to create this program. Okay, let's try to take this program and save it somewhere into here. We'll say cat into mycmd.sh and paste this command, and let's try to execute it first. So to execute something in Unix, first you have to change its mode to execution. Now let's try to do this. Okay, is what? All right, let's just put some kind of data and give it to mycmd.sh. So, okay, you can see that now. It has cleaned up the data and converted into one word per line. Happy? Sandeep is saying he's trying to replace all letters with new line. What's wrong with this command? All right, that's okay. That will actually delete everything in the input. All right. All right. I think we should put stop right now because it's beyond the time limit and other people have to leave. Okay. So we'll continue from here tomorrow. All right. See you then. Bye bye. We'll continue from here tomorrow. No worries. Good night. Bye, Lloyd. Bye, everyone. We'll continue our MapReduce in Java and the other advanced concepts of Java. We'll continue from here, don't worry. Okay, so tomorrow's session is important, so be there. All right, bye bye.